So it ends up that we're going to be able to tell whether a graph is increasing or decreasing or neither, just based on its derivative. And so what we have here is a sketch of f of x, and we're going to look at f of x at three particular points here. X1's the first one, and let's sketch in, or try and sketch in, the tangent line. Okay, it would look something like this. Okay, and you can see that this line here has a positive slope, okay, which means that the derivative here is also positive. Let's go ahead and fill this in. So if f prime of x1 is greater than 0, then f of x is increasing at x equals a. All right, so next, let's look at the slope of the tangent line here at x3. We're going to skip x2 for a second. So I've made an attempt at sketching the tangent line there. And you can see, looking at that the slope is negative. So that means our derivative is less than 0 there. So if f prime of x3 is less than 0, then f of x is decreasing at x equals a. And there's technically a third case in here. At x2, you can see we have a horizontal tangent line. We have a slope of 0, and it's neither increasing nor decreasing. We're on to example 4 here. Why don't you pause the video and give this one a try without my help. Now that you've maybe given it a try, there are two things that I think help a lot. Trying to find where the derivative would be 0 and trying to find where the derivative does not exist. Those features are usually enough for us to be able to match each graph to its derivative. And let's start off with an easy one. So here, 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 and here are all sharp corners, which means that the derivative does not exist at those points. And in between those discontinuities or places where the derivative doesn't exist, okay, and when I say discontinuity, I meant discontinuity on f prime. Okay. But in between all of those spots where the derivative doesn't exist, the derivative is going to wind up being constant. So horizontal lines, right? Because all of these are linear, right? And when you take the derivative of a linear function, you're just left with its slope. Okay. So let's see if we can find anything that seems to fit that description. So f here, I see a bunch of horizontal lines, and I see these spots where the derivative doesn't exist, a bunch of them. Okay. So f and b correspond. Let's just write the f up here. There we go. Let's, why don't we do the other one that's linear here? There's only two that were just made up of linear functions. So there should be another one below that it just has a line, some positive number, right? Because this is, again, a linear function here, this part of it. So we should expect some horizontal line that's some positive number. And for the second piece here, actually the slope of that is 0. So once we hit really this intersection, we should see just the line y equals 0 for the derivative. Let's see if we can find that. Right, and D looks like it fits that description. And you can even see where the derivative doesn't exist. That was where those two functions met up at for the piecewise function. So D corresponds with A. Okay, let's look at C. So C, you might notice, it has a horizontal tangent line right here. So we expect that f prime of 0 is equal to 0. Now, this may seem a little problematic because this one also has the same feature. But there is something that's going to make these easy to distinguish. So this upper half of a circle here, it is undefined everywhere outside of this circle. So if it's undefined, it's not even going to have a derivative outside of this region. However, this one will. Okay, its derivative will exist outside of really actually any x value you pick. So let's see if we can actually do both C and F here. So if we move down here. So let's first find something that satisfied f prime of 0 equals 0. Okay. So we want something that goes through the origin, and I see two of these, B and E. Now the next thing is we said that one of these, right, its derivative wasn't going to exist everywhere, and that was for the circle. So E here goes with the circle, and this one's going to go with the other one. Okay, so let's bring E up, write it in here. So E and let's go remind ourselves of which one was going to go with C here. That was B, the other one that went through the origin. Capital B. Right, and then there's just two more left. There's a really easy way we could do this. I see that we have this sharp corner here. This is actually called a cusp. And so at this sharp corner, the derivative is not going to exist. And this one over here, the derivative exists everywhere for this one. This is nice and continuous. Has no sharp corners. And it also doesn't have any vertical tangent lines. All right. So let's find what we have left here. So we have used up quite a few of these, haven't we? We've used up B, we've used up E, F, and D. And you can see there's only one left whose derivative doesn't exist at x equals 0. So C is going to go with D here. Let's write that in. C. And then that must mean that this A and E go together. Now, that was being, we were pretty tricky about this. We didn't actually look at that many points. But we could have done this and been a little bit more careful. And I'll show you what I mean here real quick. Let's maybe compare these two here. A and E. So notice that graph E here of f, it is always increasing. It's always increasing. So that means its derivative is always positive, and you can see A here, the graph is always positive. And if we were to compare these two now, the graph of f here, well, it's decreasing, right? Decreasing first. And I pointed to B there. I really wanted to point to this right here. There we go. Yeah, it's decreasing, so that means the derivative would be negative, and you can see it sure is over here. And on the other half, it's increasing, so you'd expect the derivative to be positive, which we can see it is here. But usually, just checking where the derivative should be 0 and where it doesn't exist is usually pretty quick.